if you just, look around you right now, how much the data that's streaming around you is visual or video?
It's almost everything.
It's almost everything. It's not just a part of our world anymore. It is our world. You've got social media feeds, TikToks, but also, industrial sensors, autonomous cars.
Even the security camera on your front door.
Exactly. It's this absolute tsunami of visual data, and trying to get real actionable meaning out of it, that takes some serious computational muscle.
And historically, that muscle has been kept under lock and key. We're talking about the most powerful vision language models, the VLMs, that can watch a video and tell you exactly what's happening.
Right.
But the problem, the big problem, is that the models that consistently set the benchmarks, the ones from the huge tech corporations, they're completely proprietary.
Meaning you can't see what's inside?
Nothing.
Yeah.
You don't get the weights, you don't see the data they trained on, and crucially, you don't get the training recipe.
And that lack of transparency, it's not just, an inconvenience. It's a huge roadblock for open scientific research.
It is.
If you can't see the data or the method, you can't verify the results, you can't debug for biases, and you certainly can't innovate on your own.
Precisely. And that proprietary dominance is exactly what the Allen Institute for AI, or AI2, is challenging with their new model series. It's called Molmo2.
Okay, so let's really unpack this. This is a monumental effort. Our deep dive today is all about the mission behind Molmo2, which is to create a fully open weight, open data, and open code solution for video understanding.
And a state-of-the-art one at that.
Right, and here's the real twist. They did all of this without relying on distillation.
Yeah, and that's the key. Distillation is that practice where you train your open model using data that was actually generated by one of those secret, closed, proprietary models.
So it's not really open at all.
It's tainted. They basically built their house from the ground up with completely open materials.
It's a really profound commitment to truly open science.
And they didn't just release one model. They released 3 different flavors of Molmo2.
Okay.
So you have a 4B and an 8B version, and those are built on the Qwen 3 language model. But then, and this is important, they also released a 7B model that's built entirely on the Olmo LLM.
And Olmo is AO2's own fully open language model.
Exactly. So that 7B model proves that the architecture is versatile, that it can work beautifully on a foundation that is, open in every single sense of the word.
And for you listening, the most critical concept to get here isn't just that it watches a video, it's how it processes that information. The core capability that Molmo2 just nails is something called grounding.
Grounding.
So what does that mean? It means it doesn't just give you a narrative answer, like a story.
Right.
When you ask it a question, it explicitly links your language, your query, to the precise where.
The spatial coordinates.
And the precise when, the timestamps. It can actually point to the answer in the video.
And that ability to point, that's what separates a descriptive AI from a truly useful operational one, especially for things like robotics or, advanced analytics.
Absolutely. So for the rest of our deep dive today, we're going to dissect exactly how AI2 pulled this off. We'll start by looking at the novel data sets they created. I mean, the sheer labor involved is incredible.
It really is.
Then we'll get into the clever architectural tricks they used for efficiency. And finally, we'll look at the results from their benchmarks and their human evaluations, which are, well, they're surprising.
And you'll see just how much harder video understanding is compared to just looking at a static image.
So where do we start? The skill set.
Let's start with the capabilities. Let's shift gears and just dig into the Molmo2 skill set. What can this thing actually do that goes way beyond a basic what's happening in this clip kind of question?
It seems like it was really built for versatility, right? Integrating that complex temporal reasoning with just standard visual skills. So what are some of those standout functions?
The versatility is staggering.
Yeah.
It really is. It covers the full spectrum. Everything from super long, dense, descriptive paragraphs down to very targeted short answer retrieval. So take captioning, for example. It's not just generating a generic one-liner.
Give us an example of that depth.
Absolutely.
Yeah.
The model can look at, say, the interior of a wide-body airliner and then produce this caption that just meticulously details everything. The red carpeting in the aisles, the exact shade of the seat upholstery.
Wow.
The precise configuration of the overhead bins, even distinguishing between the 2 seat rows on the side and the bigger rows in the center. It's long-form description that would rival a trained human observer.
That level of detail is just immense. It's going beyond just identifying seats and aisle into material and spatial awareness. I remember seeing another example about a vehicle.
Yes, the long-form analysis of the Jeep. It describes a black Jeep Cherokee XJ, so it gets the model right, not just Jeep. It notes the characteristic boxy body style. It specifies the large, aggressive tread tires. And it even details the heavy-duty black steel bumper, which has a visible mounted winch on it.
So it's doing fine-grained recognition, identifying specialized aftermarket equipment.
Exactly. But then, and this is a beautiful part of the VLM, it has to be able to pivot on a dime. It has to go from that almost poetic, verbose description to retrieving a single data point.
Like a number.
Exactly. It needs to handle short answer QA that requires OCR, or just precise numerical retrieval from a complex scene, like a financial report or a street sign.
Yeah.
It can be asked, how many digits are in the case number on the report page? And the answer is just 11.
Simple.
Or what number's on the plaque in front of the house written in gold? And the answer is 2. The way it seamlessly shifts between that narration and this pinpoint retrieval shows you just how robust its internal representation of the world is.
And this is where the video element just complicates everything. Spatiotemporal localization. In a video, things are moving, they're appearing, they're disappearing. The model has to track an identity across time.
And this is where Molmo2 really starts to shine because of its forced structural output.
What do you mean by that?
So take a query like, how many different bisons are visible in the video? A typical VLM might just spit out a number, 16.
Okay.
Molmo2's response, though, it lists the key timestamps where it confirms different bison. It'll say T.5s, TA32.1s, T70.3s, and then it concludes there are 16 bison in the video.
So it's showing its work. That structural output is vital because it proves the model isn't just guessing or, looking up a number from some external data set. It's performing true temporal grounding.
It's justifying its count.
Right, by connecting it to specific moments in that video stream.
And that temporal understanding goes even further into behavioral analysis. They call it action sequencing.
So tracking movement.
Complex human movements. For example, describing a soccer goal celebration. Molmo2 gives you the whole sequence of events. The player wheels away from the goal area, flashes a brief tongue-out grin toward the flank, and sticks 2 fingers up toward the seating area.
It's breaking the action down to discrete, ordered components. That's so much more insightful than a basic summary like the player celebrates.
It is.
And that leads us right into its core strength, the precision of grounding. If you're aiming for operational usefulness like monitoring machinery or guiding a robot, you need a model that can do more than just describe. It needs to physically point to things with accuracy.
This grounding ability, this is their major competitive differentiator. They realize that if you structurally constrain the model to output spatial data, it forces its internal attention mechanisms to be more precise.
So let's dissect the technical side of this, because the output format is, well, it's pretty ingenious. It's this compressed, plain text thing that looks kind of like an HTML tag, points chords.
Right.
Walk us through what's actually packed into that little string.
That simple string is incredibly dense with information. First, it has the timestamp, which is crucial for video, and it's often down to 1/10 of a second.
Okay.
Then it has a unique integer object index. So that's the sequence ID for that specific object instance. And finally, you get the normalized doxy coordinates. They normalize everything to a 0 to 1,000 scale, which makes the location data model agnostic and really precise.
Okay, hold on. I want to pause on that unique integer object index. If every distinct object gets a sequential ID starting at 1, that sounds like it immediately helps with robust counting.
It does. And that was one of their most significant insights from their ablation studies, when they test different components of the model. They found that forcing the model to perform counting by pointing was just vastly superior to asking it to predict a number directly.
Why? Why is showing its work so much better than just giving the final answer?
Well, because predicting a raw number lets the model hallucinate, or just generalize based on language cues. If you ask it to count the mountain climbers, and it's just predicting a number, it might pull a count from its general knowledge.
Right.
But if the model is structurally required to output coordinates for each climber, coordinate set 1, coordinate set 2, all the way up to coordinate set 5, it's proving it has spatially identified and localized every single one.
So the highest object index it lists, that just is the final count.
That becomes the definitive count. It forces accountability into the model's reasoning process.
And that structural requirement just fundamentally elevates the performance, which is what we see in the benchmarks, right? The gap between Molmo2 and its competitors on these pointing tasks it's huge.
It's absolutely enormous. If you look at the dedicated image pointing task, Molmo2 leads the point bench leaderboard. It outperforms models that were specifically designed for pointing, like POF.
Wow.
But the video pointing benchmarks, that's where the rubber really meets the road. The Molmo2 4B model got an F1 score of 39.9.
And just to remind everyone, F1 is a combined measure of precision and recall.
It is. Now, to put that 39.9 score in perspective, a major competitor, the Qwen 3 VL8B model, which uses an even larger language model as its base, scored a tiny 1.5 F1.
1.5. That's not just a small difference. That suggests the other models either can't generate the pointing output correctly at all, or their grounding is just wildly inaccurate.
It's a different class of performance. That 39.9 shows that their training philosophy, centered on this structured output and their high-quality data, it paid off.
Yeah.
Radically better.
It's the defining feature.
It is.
And these unique object IDs, they're not just for counting. They're the linchpin for the next critical step in video analysis, temporal tracking and re-identification.
Correct. For a moving scene, whether it's tracking individual penguins underwater or a horse crossing a stream, the model uses a similar structure, but it changes the tag to track chords.
And the key is maintaining that unique object ID across multiple timestamps.
That's the crucial part. Maintaining that consistent, unique ID, potentially over minutes of video. If object number 3 is a specific penguin, object 3 has to remain that same penguin, even if it swims behind a rock for a few seconds and comes out the other side.
That sounds technically really difficult, especially if there's occlusion or if two very similar-looking objects cross paths. How do you even measure the quality of that kind of tracking?
So they turned to a highly specialized metric. It's called the HOTA score. That's high-order tracking accuracy.
HOTA.
And HA is great because it doesn't just measure whether you track something. It measures two separate but joint concepts.
Okay, lay those out for us.
So first you have detection accuracy, DDA. Pretty simple. Did the model correctly spot the object in the right frame at the right time? That's the basic visual test.
Right.
Second, and this is much harder, is association accuracy. Did it maintain the correct object ID consistently over time? It heavily penalizes any identity swaps between objects.
And HOTA combines both of those.
It jointly optimizes for both. They adapted the score for their point-based tracking by defining a match as when a predicted point falls precisely within an object's ground truth segmentation mask. This methodology is how they can prove Molmo2 is performing reliable re-identification over time, something that models that just output a static count could never claim to do.
Okay, that gives us a really powerful view of what Molmo2 is engineered to do. Now, let's pivot and look under the hood. If that's the capability, the next logical question is, how do they even build it?
Right.
We need to dive into Section 2, the Molmo2 training recipe, the data and the efficiency innovations they use to achieve this without any of those proprietary shortcuts.
And the foundational philosophy here is probably the most important part of the entire project. The researchers are explicit about this. Many of the current open-weight models rely heavily on data generated through distillation.
Using closed models like GPT-4 or LLMA3 to create their instruction data.
Exactly. And that practice means those open models are just inheriting the inaccessible biases and the capabilities of those closed systems.
So if you're truly committed to open science, you just can't use that stuff. You have to start from scratch, which sounds like a Herculean effort.
It was. They had to create 9 brand new data sets. 5 were rigorously human annotated, which is incredibly expensive and slow, and 4 were synthetically generated.
But, and this is the key, they used their own open video captioner, Molmo2 Cap, for the synthetic data generation.
Yes. That ensured a fully open pipeline from start to finish. No external proprietary influence.
So let's start with the human-centric data, because that's where the quality control really begins. They focused on high-quality Q&A with a dataset called Molmo2 Ask Model Anything. And they made it a point to avoid simple questions.
Absolutely. The whole collection process was designed to elicit non-trivial reasoning-based questions. They actively filtered out anything that was vague, too easy, or just simple counting. They didn't want the model wasting cycles learning things a toddler could answer.
So how did they structure that process to guarantee that complexity? It sounds like you'd need a pretty sophisticated feedback loop.
They did. So first, a human annotator would watch a video segment and write a complex, non-trivial question something requiring temporal or fine-grained understanding.
Okay.
Then an LLM would provide a draft answer. But crucially, Human workers were then brought back in to iteratively refine both the final question and the final answer in a dialogue with the LLM.
Ah, so it's a conversation.
It's an iterative refinement loop, and it was essential for generating these really high-quality, high-relevance examples that push the boundaries of visual reasoning. It's way beyond simple object ID.
That's fascinating. So it's human-in-the-loop validation, but applied to the question itself, not just the answer. Now, shifting to the grounding task, they needed pinpoint, accurate location data for training. That brings us to Molmo2 video point.
And video point was just pure, painstaking labor and precision. Workers were required to watch videos, capture the relevant screenshots at the exact moment an action or object was salient, and then manually annotate points on every single relevant object instance. They recorded the precise video timestamp and the normalized coordinates for each one.
I have to stop you there. Isn't manually pinpointing objects in videos just incredibly tedious and expensive and slow? How did the researchers justify that trade-off? Committing to that intense human quality versus the massive scale that proprietary models get from using automated, distilled data.
That is the core economic and scientific challenge they faced. They recognized that while human annotation is slow, it provides a level of semantic fidelity and accuracy that distilled data just often lacks.
It's more reliable.
Much more. They trained on examples with up to 60 points annotated per frame, and they even included multi-turn conversations about the same video to make sure the model could handle iterative queries, like find the pepper in the colander, and then, okay, now which one of those peppers is the reddest? This dedication to fidelity, even if it limited the scale, was just non-negotiable for them to prove their open science thesis.
Okay, so high-quality human data sets, that baseline, but you still need massive scale to train a competitive VLM. Since proprietary distillation was off the table, how did they create these huge synthetic data sets without bringing in that external bias?
This is where their clever synthetic data pipeline really kicked in. They generated 4 major synthetic data sets to scale up the video Q&A task.
Let's start with Molmo2 Cap QA and Subtitle QA. How did they generate 1 million QA pairs without just getting generic, low-quality output?
The trick was in the segmentation. They used their own Molmo2 Cap model, their open video caption or caption segmented video scenes, rather than trying to describe a whole long, sprawling clip at once. By focusing on smaller, logically coherent scenes, they encouraged the model to generate these highly detailed descriptive captions at the scene level. And then those detailed captions were fed to an LLM to generate the 1 million QA pairs.
So focusing on segments keeps the model from getting lost in the temporal weeds. What about the 300,000 pairs from Subtitle QA? That sounds like it's combining 2 different modalities.
It is. For Subtitle QA, they used audio transcripts from Whisper 1, which gives you really high-quality linguistic context. Then they prompted their LLM with both the visual content and the transcript.
So the questions require combining the 2.
Exactly. It generated QA pairs that required the model to synthesize information. Reasoning over the visual context, like what color is the boat, and the linguistic context, what did the speaker say about the condition of the hull? It forces multimodal reasoning.
And they didn't just stop at video. They also specifically tackled complex reasoning over text-rich images.
That's the Molmo2 Syn multi-image QA dataset. They created 188,000 synthetic examples focused on these really complex, data-dense inputs. Think financial documents, flowcharts, tables, diagrams.
And the queries were complex, too.
They required multi-step reasoning. You could have a query that asks the VLM to combine data from 2 different images, something like based on the service pricing guide in image A and the customer service protocol manual in image B, what's the final approved refund amount, and does it need a manager's approval?
That's a real-world, high-value skill. It's simulating the kind of task an employee might actually face, juggling several documents at once.
Exactly. It moves way beyond simple OCR into cross-document inferential reasoning.
All right, we've established the massive commitment to data, but training these huge models on, 16,000 token sequences is incredibly resource-intensive. That brings us to the engineering brilliance required for training throughput. Let's talk about packing. Why was that so necessary?
The need for packing comes from the fact that the sequence lengths just vary drastically. A simple text response might be a few hundred tokens. A full-length video with all its frames and subtitles and annotations can push well past 16,000 tokens.
Right.
If you use standard training, you have to pad all those short examples up to the maximum length. So we're essentially paying for blank space and just burning GPU cycles for nothing.
It's like running a full-size semi-truck just to deliver a single envelope. It's possible, but it's ludicrously inefficient.
That's a perfect analogy. So Molmo2 solved this with their dynamic packing algorithm. And this isn't some static, pre-calculated thing. It's integrated right into the data loader, and it works on the fly.
How does an algorithm pull off that kind of logistical challenge in real time?
It maintains a dynamic pool of examples in memory. When a batch is requested, it uses a dynamic programming solver, which basically a highly optimized search function, to find the best combination, the optimal subset, of short examples that can be merged together into one single sequence.
And it's trying to get as close to that 16,384 token limit as possible?
Exactly. It maximizes the total number of text tokens plus a weighted count of image crops to fit perfectly under the limit.
That sounds incredibly complex to engineer, but what was the payoff? Why was this a game changer for open research?
The payoff was staggering. A 15x training efficiency boost during supervised fine-tuning.
Wow.
For an open source team, where computing resources are always the bottleneck, a 15x efficiency increase is just transformative. It meant they could average about 3.8 full examples into one 16K token sequence, just maximizing the use of that GPU memory.
So that efficiency gain essentially bought them 15 times more training runs for the same budget.
Pretty much. They noted that extracting the frames from the video itself was still the most expensive part, but packing ensured that every computational step after that was fully utilized.
Okay, so related to this packing challenge is how they structure the data internally when you have multiple annotations for a single visual input. They call these message trees.
Yes. The message tree is a conceptual framework for managing this complex, multitask data. When a video has multiple annotations, say 3 different QA pairs and 1 pointing instruction, the visual input itself, all the frames and image tokens, that's designated as the root message.
Okay.
Each individual annotation, the QA pair, the pointing instruction, becomes a separate branch connected to that root.
And the clever part is managing attention within that structure. You don't want the different branches talking to each other, but they all have to be able to see the root.
Precisely. They use these custom, carefully engineered attention masks, and these masks enforce that rule. They prevent the different annotation branches from seeing or attending to each other, so the tasks stay independent. The masks explicitly allow the image and frame tokens, the root, to cross-attend to all the branches. This improves information utilization because the model is processing multiple distinct learning signals for the same visual content at the same time without corrupting the individual tasks.
That is meticulous engineering. Okay, finally, let's talk about token weighting. This deals with the problem of balancing the loss function when your outputs vary so wildly in length.
This is a crucial protection mechanism. You have to have it when you're combining descriptive and retrieval tasks.
Sure.
Imagine in the same batch, you have a long video caption that generates, say, 4,000 tokens of output. And then you have a simple multiple choice question that generates just 1 token.
Right.
If you calculate the loss normally, those long, dense examples, even if they're sampled rarely, they contribute the vast majority of the loss calculation.
So the long captions are basically shouting over the short answers during training. They're disproportionately influencing the model's weights.
That's exactly right. The model learns to optimize for being verbose, because that's what dominates the loss. And as a consequence, its performance on essential short answer tasks just degrades drastically.
So how do they damp that shouting? What do they do to balance the influence?
They applied 2 key adjustments to the loss weights. First, they used a fixed, very low weight, just 0.1 for tasks that are inherently verbose, like the video captions and the detailed pointing outputs. They just accepted a lower loss contribution from those tasks to protect the others.
Okay.
Second, for all the other tasks, especially short answer QA, they implemented a heuristic based on the square root of the number of answer tokens. The formula was $4 squared all.
Why the square root function specifically?
The square root is just mathematically really well suited to managing magnitude. If your answer has 100 tokens, the raw loss could be massive. But if you take the square root of 100, which is 10, you scale that contribution way down. The $4 squared all coefficient helps normalize it further.
So it makes sure that a long-ish answer doesn't overwhelm the loss, but also that a single token answer isn't just totally ignored.
Exactly. It's a sophisticated way to find equilibrium in a loss landscape that's just dominated by token cap variance.
That truly is a masterclass in efficiency and data management. It proves that an open approach, when it's executed this brilliantly, can absolutely compete. So now let's look at the results. Let's move on to section 3, model performance and long context innovation. Did all this open source effort actually pay off on the cold, hard benchmarks?
The headline is unequivocally positive. Molmo2 isn't just competitive, it's demonstrably state-of-the-art among open weight models. It robustly outperforms previous open data models, including their own earlier Molmo2 series.
So where did it shine the brightest on the numerical scores?
Its general QA capabilities were a massive strength. It got state-of-the-art performance among open-weight models on benchmarks like VQA, V2.0, and real-world QA.
Which confirms that their complex human refinement strategy for the QA data really worked.
It did. And we also know that counting is a formidable strength, which aligns perfectly with its grounding focus. It performed exceptionally well on the really challenging Pixmo count test set.
And the beauty of the Molmo2 approach is that the underlying language model foundation, that stays strong.
That's right. The Molmo2 4B and 8B versions performed comparably to their powerful base LLMs, Qwen 3, on pure language tasks like math and general knowledge. In fact, they even performed slightly better on the ARC challenge, which tests abstract reasoning.
So the vision training didn't compromise their linguistic capabilities.
Right, which is a common fear.
But when you're pushing the frontier, you're going to find gaps. If it's so efficient and so focused on precision, why is the model still lagging in some of these specialized tasks? Where did that performance gap show up?
The gaps were noticeable in areas that require really complex, specialized multimodal reasoning and heavy OCR. The model is a bit behind the best open-weight models on benchmarks like MathVista and MMMU.
And what are those testing?
They demand complex mathematical problem-solving that's integrated with visual data. And they also noted struggles on OCR-heavy tasks, specifically DocVQA and InfoQA.
So what are these benchmarks testing that Molmo2 hasn't fully mastered yet?
They're testing true inferential reasoning under specialized constraints. MathVista, for example, it requires you to read data from a graph or a chart and then perform multi-step arithmetic operations based on the data you extracted.
I see.
And DocVQA is about reading complex document structures like tables with nested headers. It suggests that while their synthetic data efforts were impressive, these highly specialized domains, where the text is often small or blurry or formatted nonlinearly, they still need more targeted training data.
And possibly dedicated pre-processing pipelines.
Possibly. The current efficiency gains are not yet translating perfectly to that kind of highly domain-specific acuity.
Okay, let's move beyond the raw technical scores and talk about the ultimate metric, human preference. How did Molmo2 actually fare in direct comparison tests against the proprietary giants?
They conducted an incredibly rigorous human evaluation. They collected 450 unique open-ended questions based on videos and gathered over 105,000 pairwise ratings from human evaluators.
Wow, 105,000 ratings? That's a huge volume. How do you even process that many pairwise ratings into a definitive ranking?
They used the Bradley-Terry model to calculate an ELO ranking.
Like in chess?
Exactly like the ranking system in competitive chess. If Model A is preferred over Model B 70% of the time, Model A gets a higher ELO score. It's designed to give you a statistically robust measure of qualitative human preference.
So what did that ELO ranking tell them? Where did Molmo2 land?
Molmo2 8B ranked 5th overall, which places it right there in the mix with models from the major corporations. But critically, it ranked first among all the models that rely purely on open data.
That's a huge win for them.
It is. And for the open-ended QA cast specifically, Molmo2 8B showed a clear advantage over the Qwen 3 VL models it was competing against, even though they use similar base LLMs.
And their pairwise win rates, they confirm this competitiveness.
Yeah, right. Absolutely. The Molmo2 8B model achieved a 53% win rate head-to-head against the Qwen 3 VL 8B model. And even the smaller Molmo2 4B model won 51% of its comparisons against its counterpart.
So that shows that their training methodology, the structural changes, and the open data philosophy, it translated into answers that humans actually preferred.
A genuine competitive edge.
Yes. What were the qualitative insights? What did the human raters actually say? Why did they prefer Molmo2's answers?
The feedback was really illuminating. Humans preferred Molmo2's answers in QA because the model was just smart about its verbosity. It gave detailed explanations when the question required complex reasoning, but it stayed concise when a simple, direct answer was enough.
So it matched its verbosity to the user's need better than its competitors.
It did. However, the raters also pinpointed a weakness. The model sometimes struggled with long captioning tasks. It would occasionally produce repetitive or even nonsensical content near the end of a really long output.
And what's the suspected cause of that? Is that a Molmo2 problem or a foundation model problem?
It's likely a bit of both. The foundation LLM itself, Qwen 3, has a known tendency for repetition or, divergence during extremely long generation sequences.
Okay.
And compounding that, the Molmo2 team noted that the amount of high-quality captioning data they had was relatively limited compared to their QA data. So the model just didn't have enough fine-tuning to really stabilize its long-form generation ability.
Let's shift now to what might be the single biggest operational challenge in video understanding: processing extremely long video contexts efficiently.
Mhm.
I mean, analyzing a 5-second clip is one thing. Analyzing a 5-minute recording of a construction site is exponentially harder.
The challenge is fundamental. It's physical. It's computational constraints. To analyze a long video thoroughly, you need to sample a lot of frames. But every single frame you sample converts into a massive number of visual tokens that get fed into the language model.
Right, and even with our dynamic packing, the system has a hard cap. You're limited to around 600 visual tokens.
Exactly.
So how do they maximize understanding for those long videos without just causing an overload?
They employed the sophisticated test time strategy they call slow-fast encoding. The concept leverages resource allocation by varying the pooling strategy for different frames.
Okay, break that down.
Think of it like a camera operator deciding where to use a high-definition close-up lens versus where to just use a grainy wide shot. Every frame is represented, but it travels down one of two pathways.
The slow or the fast pathway?
Right. The slow pathway uses high spatial detail 3x3 pooling, so you get a sharp close-up. The fast pathway uses low spatial detail 9x9 pooling, which gives you a blurry, grainy background check. And this choice is governed by a periodicity parameter in token dollars.
So it effectively spreads the token budget. But if you just select the high detail frames arbitrarily, you might miss the important action. The real innovation, the crucial improvement, was making that selection intelligent.
That is the absolute key, query-based selection. Instead of just periodically selecting, say, every 10th frame for high detail, which is the standard approach, they use the text query itself to inform which frame should get that expensive high detail treatment.
That is incredibly smart. How does the query actually translate into a selection mechanism?
So the model first embeds the text query, and it embeds every single frame in the video. Then it calculates the cosine similarity score between the query embedding and each of the frame embeddings.
And cosine similarity tells them how conceptually close the query is to the content of a specific frame.
Exactly. The highest scoring, most relevant frames are then dynamically selected for that high detail, slow pathway.
So if the question is about the worker wearing a red helmet, the model makes sure that the 3 frames where that worker is clearest get the high-resolution treatment, and it effectively ignores the irrelevant frames in high detail.
Precisely. It's optimizing its limited GPU memory based on semantic relevance. And the results show that the standard periodic sampling actually hurt performance on long videos. But using this query-based selection gave a significant boost to long video understanding, with only minor acceptable regression on short videos.
And it reduced the token count.
It did. It efficiently closed that performance gap while reducing the total number of visual tokens needed by about 43%. It's efficiency optimized for intelligence.
That is a perfect demonstration of how targeted architectural innovations can overcome these massive computational bottlenecks. Okay, let's synthesize everything we've covered and conclude this deep dive into Molmo2.
I mean, Molmo2 stands as a major scientific achievement. It's not just a competitive model. It is a proof of concept for open science. It demonstrates definitively that state-of-the-art video LMs can be built without relying on those proprietary, opaque, and potentially biased data distillation pipelines.
And the core technical achievement is that synthesis of their whole training strategy. We saw those revolutionary efficiency optimizations like dynamic packing, boosting throughput by 15x.
A huge win for open teams.
And that infrastructure supports a superior grounding capability, enabling that precise pointing and counting that other open models just can't seem to match. That massive F1 score difference is the proof.
And yet, the AI2 report is impressively candid about the limitations that still exist. They noted that video grounding is still just fundamentally challenging. It remains less consistent than image grounding.
Right.
We noted that even Molmo2, despite its superiority, didn't get accuracy rates above 40% on key video grounding metrics. You see 70–90% accuracy on similar image tasks.
So why is that gap between video and image still so dramatic, even for a model this good?
It really boils down to two main factors. Both are tied to just inherent complexity. First, video analysis demands processing vastly more content. It's just computationally harder.
Then second,
and most critically, video requires robust re-identification.
Yeah.
The capacity to consistently recognize whether an object in frame A is the exact same object in frame Z minutes later. This identity tracking is a major technical hurdle. They also noted issues with having to process low-resolution frames for very long videos. And interestingly, a weakness in their tracking data itself. The point marker for a single tracked object can sometimes flicker, meaning the location of the annotated point changes slightly frame to frame, even if the object hasn't really moved.
So if the ground truth data itself flickers, the model's going to struggle to learn absolute consistency.
Exactly.
So we have world-class language models and we have excellent visual encoders, but that consistency over time, that re-identification and robust tracking across extended contexts, that is the definitive remaining bottleneck right now.
That is the challenge the next generation of researchers has to solve.
Which leaves us with our final provocative thought for you, the learner. The Molmo2 report makes it clear that the weakest link in high-performance video analysis isn't basic vision or language anymore. It's the complex, consistent, long-term re-identification and tracking of a single object across a long video brave. A weakness made worse by things like flickering point markers in the training data itself. So if the next generation of open models can solve this deep technical challenge, if they can achieve absolute point marker consistency and object identity across frames, how quickly will that single breakthrough unlock reliable general-purpose autonomous applications? Things like large-scale traffic monitoring, surgical robotics, or complex sports analytics tasks that Molmo2 is explicitly designed for but can't yet perform perfectly? Something to mull over as you watch these systems continue to mature.